Hey everybody, so this particular research paper is called Multi-Plasticity Synergy with Adaptive Mechanism Assignment for Training Spiking Neural Networks. Very long title overall. Essentially, starting off with this, I want to start off with spiking neural networks overall. And then, so to me, spiking neural networks are the most fascinating to me personally architecture outside of transformers architecture and like the kind of like a alternative architecture to transformers. And the way that I look at this and frame this overall in my head, I've kind of gone over the history of this concept a lot before, where essentially you start off with the perceptron. Perceptron was found to not work overall, so then they created multi-layer perceptrons, MLPs, that worked a lot better, but still had issues. And then they deviated from there, and then added gradient descent, back propagation, etc. And then so that brings us all of those stacking innovations bring us further away from the original concept of AI as it was originally designed, which was a biological mimicking, a computerized mimicking of the biological processes of the human brain, and then more into what AI is today, which is basically uh, overall an alien intelligence. Like that's the best way to describe it overall, right? And reason why I use the term alien intelligence within that is because there is literally no biological organism or biological basis or comparison for AI in its current form, right? But it works, and so nobody can uh, deny that it works overall. You can utilize it, you can see it, right? But the bottom line within that is that it's not biologically equivalent to anything. And why is that problematic? That's problematic because uh, transformers compared to the human brain is massive amounts of computational and energy difference, right? So uh, this we have how I look at it overall is two known variables within this, right? At this point, we know that transformers, so this alien intelligence architecture works, but it works off of massive compute and massive amounts of energy. And then we also know that the human brain works and biological brains work, and biological brains work off of very little compute and the extra electricity of like a light bulb. And then so there's a gap there, right? And then so spiking neural networks to me are the closest research area that we have at the moment to more on that gap side, like more on the biology side, right? Spiking neural networks are very specifically based off of like neurons and like how they work and the spiking of a neuron, right? And essentially, the spiking neural network has only two modes, 0 or 1, on or off, right? And then essentially, I'll dive deeper into this, but essentially, you go through and you pass the energy through it or waves through it. Uh, if those get big enough, they kind of spill out of the bucket, and then that turns it onto a 1 and it makes it spike. And then that's essentially how these neurons work, which is like essentially like within that a lot of similar processes to how the brain works and how the brain functions overall, which is why these networks are great. But what we can't figure out overall within these spiking neural networks is how exactly and what exactly is the best way to train them. And so that's where we're at within this, and within this particular research paper especially, that's what this goes into, right? And then so the first is that it introduces spiking neural networks. It gives kind of an introduction, kind of the same introduction that I gave here, right? That they're biologically inspired, and that there's big methods within them, but that they're hard to train overall. And then so essentially what they do is in typical fashion for training these models, it's you have like one of three options, or like one of a few different options. But so what they do within their particular framework, this multiple plasticity synergy learning, is that they combine three of these frameworks overall, and then they combine them into a singular model at the end. So each one of these methods is trained individually, and then there's an output score for each one of these individual methods, and then they're combined into kind of like layers of the network, and those are STBP, Hebbian learning, and SBP. And then so overall, essentially within this, they provide their framework here. So it's they propose a biologically inspired MPSL framework for spiking neural networks motivated by the phenomena of neurotransmitter coexistence. This framework enables multiple learning mechanisms to collaboratively guide the accumulation of information while preserving their distinct update behaviors. Kind of the bottom line within this and within that is, so since the advent of AI, we've learned more about how neurons function and how neurons operate. And then not every neuron is equal. Not every neuron operates and fires the same way, and not every neuron operates and fires off of the same criteria. And then so that's kind of the logic within this, right? Is that so like each one of these different neuron layers that learns off of these different methods becomes in the end like a different type of neuron, right? And then so then you combine those, and then neurons that fire together learn together, and then so by doing and combining those layers together, this system learns in tandem, right? And then so it allows for a hybrid system and a hybrid learning system, which is essentially what their goal is within this, right? And then so here's kind of the overall framework within this, and so it's it's pretty simple as far as the diagram, right? You have three different layers. So you have your input, and then it goes through the three different spiking layers, and then it produces the output. And then within each one of these individual layers, you've got your input, and then you have your semantic weights, which, weight, like parameter weights. And then from those, like the main goal is this membrane potential update, right? And that's kind of how these function, how a spiking neural network functions, is it's based off of membranes, right? Like, so again, in the 1950s, our understanding of neurons and how they worked was fundamentally wrong. and then so that's what led to a completely divergent path. Whereas spiking neural networks, spiking neurons are what if we continued along the path of our actual understanding of how neurons actually work, and then we continued along that path, and that's essentially what you get within this, right? And then so the concept that they're trying to work around within this, and the big thing with spiking neural networks is this synaptic plasticity, right? We don't know how to solve for this in spiking neural networks, and we don't know how to solve for this in AI overall. Like, this is the biggest problem within AI overall, right? We'll call this more generalizability. Like, how do you make it the model generalize more? And then to me, it's very apparent at this point, going through all of these things, that the bottlenecks are within the training methods overall, right? That's just the simple conclusion that I can draw within this. So within this, so essentially you have Hebbian learning, which is probability-based learning would be like the most simplistic way to do that, or to explain that. And then the other two methods are backpropagation-based methods, right? So those other two methods, the other two training methods within this and within this overall design, are not biologically inspired. We're again diverging from biology with those other two methods. And then why are we diverging from biology within those other two methods? Because those are the two methods that we know work within this, right? Like, I mean, backpropagation is I can't overstate the significance of backpropagation when it comes to training of these models, right? Like, without backpropagation, these models don't work very well. And even within a spiking neural network, right? And then so, but then that brings up that lingering question, and going back to the question up front within this, is that the brain itself doesn't do backpropagation as we're doing it computationally within this. The brain does do a backpropagation style method, but it's not pure backpropagation. So I think it is important to highlight that, right? Like, when people say that the brain does absolutely no backpropagation methods, that's not 100% accurate. Like, it doesn't do pure backpropagation, and it doesn't do anything near as we've laid out within this here. So before the next step, I'll dive into the actual demo of this model. But before I dive deeper into that, I want to give you just kind of a deeper explainer here of spiking neural networks, because I assume that's going to be like a lot of the broad interest for this video, and then a lot of people come into that for this overall. So spiking neural networks are a class of artificial neural networks that bring time into the picture. Instead of passing around continuous numbers like ANNs do, or CNNs, they communicate using spikes, or brief binary pulses inspired by the way that biological neurons fire. And then so what makes SNNs different? ANNs, or standard deep nets, they function so that neurons output continuous values or real numbers. A ReLU or sigmoid transforms the input into an activation. Whereas SNNs, the neurons integrate inputs over time into a membrane potential. When this potential crosses a threshold, the neuron emits a spike, or a 1, otherwise it stays silent or 0. So think of SNNs as event-driven. Instead of always computing, they only fire when something significant happens. And then remember that part where I mentioned that the training methods that we have even for SNNs are divergent from biological systems. And then so that's true within this, right? So your standard ANN uses the ReLU function, whereas SNNs do still use ReLU, and I'll dive deeper into that. They just use a form of ReLU called leaky ReLU. It's how they work, and then I'll dive into that leaky concept more because that's important here. So the core building block, leaky, integrate, and fire, or LIF neuron. So integrate. Inputs are spikes from other neurons, and they accumulate in the membrane potential. A leak is that the potential decays over time, just like a leaky bucket, right? So you fill the bucket to the top, but the bucket has a hole in it, and then so that bucket's just draining water, right? And then so fire. If the potential exceeds a threshold, then the neuron emits a spike and resets. So you're constantly filling this bucket with water, but this bucket is constantly leaking out water. But if you get that fill rate high enough so that it doesn't leak fast enough, then it turns into a 1. And then so this dynamic is what makes SNNs temporal. Neurons carry information not just in how much, but also in when spikes occur. So why spikes? Spikes bring 2 major benefits. The first is that they're very energy efficient. On neuromorphic hardware, spikes allow sparse, event-driven computation. You only compute when spikes occur. Again, going back to the human brain, spiking of neurons, that's our current understanding now of how neurons work and function overall, right? Second is temporal coding. The timing of spikes can represent information, enabling richer coding schemes than just static activations. Like, this is important, right? Like, it's this temporal coding, like the time is built into the mechanics of the spike. Like, that's this most simplistic way that I can put this, right? Like, the biggest problem with other neural networks overall is like, how do you actually get them to understand anything temporally? And we try that across the board. It's a failure. I've brought this up a lot, right? That the best methods that we have outside of this right now are diffusion models, but spiking neural networks, like temporal coding is built into the spiking mechanism itself. I find that philosophically intriguing overall, but just highlighting that. 4 challenges in training. The biggest challenge: spikes are not differentiable. You can't backpropagate through a hard threshold. So again, there's the human brain, biological brains overall, none of them backpropagate. So how do you solve that, right? And that's kind of where we've gone with spiking neural networks, is essentially solving for that problem overall, right? Which is, again, if there's a knock on this, it's like, I think that we're still missing something within that, because again, this isn't how biological brains solve this process. But so surrogate gradients, or STBP. They approximate the spike function with a smooth curve during backpropagation. Hebbian rules are local, biologically inspired learning, neurons that fire together, wire together, and then event-based learning algorithms like spike timing dependent plasticity adapt weights based on spike timing. And then so the method that we're looking at here, this MLPL method, combines all three of these methods to get the best of both worlds: efficiency of spikes plus the accuracy of deep learning. So how do spiking neural networks actually encode data? They use two common methods. The first one is rate coding, which is the more intense the signal, the brighter the signal is, the more often a neuron fires. So brighter pixel equals higher spike rate. And then temporal coding. So information is carried in the precise timing of the spikes, not just the count. So like Morse code, right? Like a flash, and then the space in between the flashes, the timing in between the flashes matters, right? And that is temporal coding. And then so it's like blue 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 would be different than like blue blue blue, right? And that type of concept. And then so in this particular demo, I'm training it so that brighter pixels fire up more frequently, and I'll show that to you. And then so the advantages of spiking neural networks are that they're low power, so they're great for edge devices and neuromorphic chips. They're event driven, so they're naturally suited to event-based sensors. They have biological plausibility. Out of every architecture around AI that currently exists, like to me, so AI in its current form is an umbrella term, and there are so many architectures, etc., that exist under this umbrella of AI that like AI as a singular unit is like a kind of a misnomer, right? So out of like under this broad umbrella of AI, the architecture that is currently most biologically plausible and has the most weight behind it is spiking neural networks for sure. And then so potentially they lead to faster inference if implemented on the proper hardware. So where are spiking neural networks currently used? They're currently used within neuromorphic vision, so event cameras that output asynchronous streams of pixel changes, in robotics for energy efficient control systems, in brain inspired computing, testing theories of cognition. So like all of your 10-year out projects are utilizing and playing around with these methods, right? And then edge AI, so low power, always on sensors for Internet of Things devices. The road ahead. Spiking neural networks are still young compared to ANNs, and the big bottlenecks are efficient training methods combining local rules and surrogate gradients, more accessible hardware support, and then bridging the gap between biological inspiration and machine learning performance. The framework that we're testing here is just one such step, showing that multiple plasticity rules working together can close the performance gap with ANNs and also transformers while keeping the biological flavor. Key takeaway, SNNs are neural networks that think in spikes, not in numbers. They bring time, energy efficiency, and biological realism into AI, but need creative training tricks to reach ANN levels of accuracy. And then that's like the bottom line within this, right? And I can't simplify and stress this enough that like essentially like we have a very good understanding at this point of this architecture, how it functions, how it compares to neurons, etc. Overall. Where we're significantly lacking still at the moment is how exactly do you train these things properly? I'll illustrate that here for you within this demonstration notebook, right? So this notebook demonstrates MPSL training for spiking neural networks, or SNNs, inspired by the paper. And then the framework combines all three of their methods that they utilize. So it's utilizing STBP, Hebbian plasticity, and SBP-like plasticity to create a set of learnable coefficients, so coefficient 1, 2, and 3, which adaptively blends the mechanisms during training. At inference, the system collapses to a single effective weight per layer, so there's no extra parameter cost. It's three weights total, right? Because each layer is one singular weight, and I'll show you the outputs of that, and I'll talk about that a little bit further here. So in here, you're going to see two cells. You're going to see the first one is my base experiment, and then I'm going to show you a few things that I did wrong here, and like how easy it is to do stuff wrong within this, and then I'll show you exactly how it works properly. And then so key ideas demonstrated within this are multi-plasticity synergy, adaptive gating, single weight inference, and flexibility. So let's go here to the actual framework itself. So the framework is pretty straightforward overall, right? It's a spiking neural network, and then it's being trained via these three methods. Each one of these methods is its own individual composite layer, and then so you train the three individual composite layers, and then at the end you combine those into a singular weight per layer, and then your end output is then combined, and then so that's what you do here. And then so you can see here's all the different methods. So we're utilizing surrogate gradient descent, which so again, like a highlight, and I want to just highlight this overall. Like, so the training methods that we are currently utilizing for this model are borrowing 100% from the training methods that we know work for deep learning. So gradient descent and back propagation and Hebbian learning very specifically. And then within that, like, we're just combining those methods into this because we know that they work within this, right? But then again, we know that this isn't the end best training result. What it is, I don't know. I think it's an important overall way to highlight that. And then so here you create the linear layer where you're combining all three of those layers together, and then you get your simple, like, this is the actual neural network itself, right? The actual spiking neural network with multi-layer perceptrons utilizing the logic and math that they have here. Our data set in this instance is fashion MNIST. We're training the data set here. I'm only training it for 3 epochs. You could adjust this. You could adjust all of this, right? Adjust the epochs, the time steps, etc. You would get better model performance overall. But in this first instance, I trained it just utilizing CPU, which took a bit of time. Like, I think it ran for like 15, 20 minutes. I fell asleep. And then when I woke up, it was done. I think it was like 15, 20 minutes. But so within this, you have epoch 1, so like epoch 1, 2, and 3, and then you have the individual layers, right? And then so we get up to, what I want to highlight here is by epoch 3, I'm up to 94% accuracy, but my post-merge accuracy goes down to 72%. Even though I'm like, each one of these individual layers here is getting 93 to 94% accuracy, but then when I combine them, like the sum of the parts is worse than the individual components, which is like the opposite of what we want, right? And then it's 72% accuracy, and then the reasoning for that is, so just like up here, within the code, and then within it's very specifically within this combination, this here, right? This layer where I'm combining all three of them. My math is a little bit wrong as to how I do the math for that combination and combining those layers here. And then essentially it's just adding and then merging them, right? And then so by doing that, it actually decreases the accuracy overall of the model, but our tests are coming out here, so we can see that the overall concept is working. And then I should highlight here, if you go to on their research paper, they're able to get up to on MNIST, they report 99.52% accuracy. And then again, so they're doing a lot more time step, they're training harder than I am, and for more time steps and for more epochs, but they train it up, right? And then so they say 99.52 on MNIST, and then so we go through here. Here's my second attempt on MNIST, and then recreating their frame. The bad thing with this is that they with their framework, they just give the math behind it, and then they give the full explanation, right? So this is like as close to reproducing it as I can, but so you could increase the batch size. So if you put this to 10 to 20, I'm assuming that's what they do, right? In the end, I just train it for 3 epochs overall, and then so I go through, I fix the math within there, and then as you can see here, so we get from our individual training of the epochs, it's a 92, 90, and 92% accuracy. And then our post-merge accuracy is higher. So, and then once we get our post-merge and fine-tune, I get it up to 95 point, we'll call it 95.78. and then they're reporting 99.57. So like it's definitely within the realm of 100% possibility to get this up to 99.57 on MNIST. I'm getting it up here to 95.58. The second time I ran it on GPU, and this took like 2 minutes to run. So like this is massively computationally efficient compared to transformers architecture. And then you're seeing here, you can look at my verified results here, 95.58% accuracy after 3 epochs within this on MNIST, right? And I'm like, my simple assumption, like very specifically and straightforward, set that, like, just go here, run it, set it to 10 or 20. Set it to 20. I guarantee, like, I'm almost positive you'll get the you'll get to where they have the 99.57% accuracy. Like, I'm positive that you can replicate their here, right here. So just literally switch this to 20. like that would be my recommendation here, right? And like, I'm positive that if you do that, you're gonna get replication of this result here, 99.52. Because it's like, I mean, it's, we're there, right? Like, I'm here basically within this. I'm like, it works. You can do it overall. Here's everything that you need. Pretty cool method overall, right? Just highlighting this and talking about this. Like, anytime that I see anything cool around spiking neural networks, I like to talk about them. There's not a lot of people that like I talk about or understand spiking neural networks overall, so they interest me. Again, this is the definitely one of the architectures, like I'd say like top 3 architectures that I keep my eye on at all times, just because it's the most biologically inspired architecture that's out there. So if you're like, I mean, if you want to, like, if you're looking to for alternatives to transformers, or just even like putting chips on betting on anywhere within that, this is the best way within there, because it's, I mean, all like all of our examples of intelligence outside of AI are all around biology, right? All around how brains work and brains function. And we know that brains work, and we know that brains function, and we know that they function very well and very efficiently. So if we can just stick as close to that model architecture as possible, to me, the big challenge is again, like, that training mechanism. Like, how exactly do these things train? And I like, my overall assumption is that they train differently depending on the modality and what exactly the neuron is, right? I'll leave here and I'll give that like as my last within this, right? If I were to guess what overall is like how to fix this training problem within spiking neural networks, I think that it's a matter of looking at this problem differently than we have been, right? So at this point, we are accepting and we are understanding of the fact that within neurons function and they operate differently, right? Like a vision neuron is different than we'll call it like a language neuron, right? Like they're two different things, different processes, and then to train a vision neuron is different than to train a language neuron, and then my assumption is that they're 100% on the right track within this, and that it's not just a matter of training the vision neuron individually and the language neuron individually, but more so the combination of training them both together. And then the very honest, simplistic example that I reference within my own thought processes around these things when it comes to this is the game of peekaboo, right? Like, so when it comes to human learning, our understanding of how that process works at the moment is essentially like babies are not born with object permanence, meaning that like a baby, when it's first born, if the mama leaves the room, the baby doesn't understand that the mama isn't there anymore. That the baby thinks it's just gone, right? Like, and so that's object permanence. And then you teach that via like peekaboo, and then like peekaboo is a very efficient way to train vision-based neurons. If you like, that's exactly what you're doing, right? Like, you're giving the baby a real-world example of here I am, now I'm gone, now I'm back, right? And you're essentially like giving it a training process that is very specifically geared towards vision learning in that overall instance. within that. And then like that training, like there's not a better training process for a vision neuron that I can think of in that instance that is attached to other neurons that will then be able to come up with a reasoning process than peekaboo game. And I think that like that's where we'll end up heading within this is different training modalities and different training methods depending on the modality of the model, and then like individualized methods that look more and more like the peekaboo game and less like just purely feeding the data through down the model's throat. Like that's kind of the best way that I can frame that overall. So I'll leave a link to this research paper as well as this explainer doc, and then the collab notebook here, and here. And then so if you like this type of content, please like and subscribe. Thank you very much.